Number 2, a bullet of mass m is fired horizontally with speed v into a block of mass m initially at rest. At the end of an ideal spring on a frictionless table. At the moment the bullet hits, the spring is at its natural length, L. Here is L. The bullet becomes embedded in the block. Now that's important because when it gets embedded, you should recognize that this is inelastic collision. And the simple harmonic oscillation result, meaning it's going to go back and forth without friction. Okay, so part A, determine the speed of the block immediately after the impact by the bullet. So I already mentioned that we need to use the inelastic collision. So mv, and because the big M here is not moving, so we will just consider it 0, is equal to m1 or small m plus big M, because now they are together as embedded system, b prime. It's asking us immediately after. B prime is our goal here. I'm gonna make it red and call it goal. So what is a b prime? Well, all we need to do is just divide both sides by the small m plus big M. Okay, so that becomes mb over small m plus big M. Okay, that's the answer for part A. For part B, determine the amplitude of the resulting oscillation of the block. Okay, let's find the amplitude. So, the amplitude will be determined after it hits the block M. So the entire kinetic energy from the big M after the collision should be converted to entirely the spring potential energy at the amplitude or maximum. So kinetic energy after it collided, or the bullet collided with the mass m on the spring, is 1/2 times small m plus big M, right? After the collision, the small m and big M are together. And then v prime squared is equal to the spring potential energy at the amplitude is at when the kinetic energy is gone. So yes, it's 1/2 Ka squared. Now, we already found B prime from part A, so we can also combine it here. So 1/2 times small m plus big M times mb over small m plus big M square, entire thing, 1/2 Ka squared. Now we need to find the amplitude. This is our goal. So we can multiply both sides by 2, and that becomes m plus big M. Now here's what we can cancel. Because m plus big M gets squared on the bottom and there's only 1 on the top, we can just cancel the top part. So we get m plus big M on the bottom and m squared b squared on the top equals Ka squared. Alright, so we can divide both sides by K, and we get A squared is equal to 1 over K m squared b squared over m plus big M. But we need to find just A, not the A squared, so we need to square root both sides. So what does it become? Amplitude is equal to, okay, we can pull out the M and B, but K and the sum of the two mass of the blocks will still remain under the radical. Okay, this is our answer. This is our answer to part B. Gotta close the parentheses. Alright, so that's part B. Let's move on to part C. Compute the frequency of the resulting oscillation. Remember from the part A, the frequency is 1 over 2 pi square root of k over m by the memory device of going clockwise alphabetically. Now the mass of our spring mass system is no longer just big M. It's actually big M plus small m. So yes, the frequency will change because the mass system got bigger. And that's your answer.